Okay, hello and welcome back to the EBD seminars. Here today we have Fernando Blanco. He has just started with us 1 month ago to work as a postdoc with Vicente García Navas, and today he's going to present us his main research line about ancient ecosystem and how this is going to intersect on what he's going to be doing here.
Well, thank you all for coming. Today I'm going to talk to you about my main research line, and which is in connection with what I'm going to do here with Vicente. So, okay. So, as all of you know, we are experiencing an accelerated impoverishment of all Earth ecosystem. Uncontrolled human development is affecting most of our ecosystem interaction, likely pushing ecosystem through an ecological threshold beyond which an irreversible will eventually happen. We define this, the ecosystem structure based on these interactions of their constituent species. In turn, these interactions can be interpreted as the role that the species perform in the ecosystem, and one way to define this role is to use characteristics of the species that condense its ecological properties, also known as functional traits. These functional traits allow us to characterize the ecosystem functional structure, and by doing so, we can study an ecosystem transcend this ecological threshold, also known as tipping points. However, in order to study this dynamic of functional structure evolution, we need to track the evolution of this ecosystem over evolutionary time. So, imagine for a moment that you will be able to see through a window and observe how the ecosystems evolve during millions of years. Well, this is what paleontology can offer us. Thanks to the fossil record, we can track the evolution of ecosystem over millions of years. Mass extinction, abiotic events, all are well documented in the fossil record. Information that is fundamental to study the behavior of ancient ecosystems under past perturbations. By doing so, we will be able to inform current conservation in order to help them to find more effective and long-lasting measures. Thanks to the fossil record, answer fundamental questions for evolutionary ecology, like how long does ecosystem functional structure typically endure? Or did the ecosystem experience moments of functional collapse trigger functional reassembly? Or what were the factors that influenced? In order to answer this question, we demand to find an analytical framework that allow us to characterize this functional structure and track the dynamics. So we can do that using network analysis. So thanks to network analysis, we can understand complex systems as ecosystems are by them into the individual components known as nodes and the connection between them known as links. This doesn't work. So using network analysis, we can study the pattern of interactions, and this allows us to study the behavior. But the first thing is, I don't know why this is not working. Anyway, to characterize or to define this community structure, we can do that using community detection algorithms, which basically find group of interconnected nodes, known as models, that you can see here in this image. So we first validate this approach using the high-resolution fossil record of the mammals of the Iberian Peninsula during the last 21 million years. So to give you an idea on how good this fossil record is, in our database we have one fossil site every 0.1 million years on average. So in total, we gather information of almost 400 species grouped in 167 localities. In order to define these ecological robot species, we also gather information for 3 functional traits. diet, body size, and locomotion. Species using functional entities, which are unique combination of these three functional traits. So just an example, this is Gomphotherium angustirem, an Asian mastodon that will be categorized in this functional entity of between 2,500 and 5,000 kilos, gross mixed feeder with other species that have the similar functional traits. So once we had all the data, we built two different types of bipartite networks. Functional networks using the functional entities and localities as nodes, and a taxonomic network using directly the species and the localities where the species were present. So this is the main result of this study. In the x-axis you can see the time, and A and B are the results from the network analysis for functional structure and taxonomic one, and on C is showing the result from diversification rates that we calculate using the software Pirate. So taking a deeper look into the graphics, the first thing that we notice is that in the functional structure, we found a module replacement every 2.8 million on average, while when we take a look on the taxonomic structure, we see that this module replacement happened 0.9 million years on average. So this is showing us that the taxonomic structure was more volatile than the functional one. So coming back to the functional structure, we identify three moments of prolonged stability, functional structural stability, that we call here functional faunas. The first one started around 18 million years ago, and will last until around 15 million years ago when the first reassembly happened, with the onset of the second functional fauna. This seems to be related to a change during that epoch to a more forested habitats. After that moment, the system gained stability that will last until around 9 million years ago with the beginning of the third functional fauna. This seems to be related with an intensification in hydric seasonality, which ultimately led to the spread of the C4-dominated grassland. After that moment, we have a prolonged stability that will last until our current days. So using a trait-dependent extinction model implemented in the software Pirate, we did not find an overall effect of individual traits or the combination over the extinction of the species. However, we found that the species attached to a collapsing functional system had higher extinction risks than the ones attached to an ongoing functional system. Thus, during moments of severe ecological shift, the extinction risk seems to be determined by the attachment to a collapsing functional system rather than by the individual functional traits. So taking a look to the third part of the graphic, we saw that diversification dynamics seems to be kind of related with the reassembly moments that we found in the functional structure. However, when we take a look on the third functional fauna, we can see here several changes in the diversity that doesn't seem to have an effect on the functional structure. So the system is resilient enough to overcome all these changes with no apparent change in terms of functional structure. So why? Why was that? Well, we took a look into the functional richness and functional diversity, and we found that the functional richness and diversity were increasing through time in the different functional faunas. So an increased functional richness with increasing functional diversity associated with persistent functional structure agrees with the idea that biodiversity enhances ecosystem resilience, also known as insurance effect. So once we validate this new analytical approach, we go for the big guys. So we apply to the terrestrial large herbivores. Since the aftermath of the KPG, they are the main ecosystem engineers They perform key functions for the ecosystem, from seed dispersal, soil compaction, and they are the biomass primary consumers among vertebrates. All of this shows the close relationship with the environment that they have. However, this is a recent decay. Once widely diverse and widespread, as you can see here in this illustration from the Miocene of South America, today they are only restricted to 3 extant groups: Artiodactyla, Perissodactyla, and Proboscis. This, adding to the high resolution fossil record that they have, makes them the ideal group to study functional structure dynamics. So, to do so, we gather information of all terrestrial large animals in this 3 order that live in the world during the last 60 million years. To do so, we gather information from online databases and a deep review of the literature, and all families were checked by a taxonomic specialist. As a result, we obtained a database with more than 22,000 occurrences, or more than 3,000 species in more than 10,000 fossil sites. In order to correct from potential biases, we grouped the fossil sites in 78 continent states, which are international chronostratigraphic chart stages by continent. So to define again the role of the species, this case, we gather information for 14 functional traits, 13 dental traits, and body size. So the first thing that we need to do is to reduce the trait dimensionality in order to understand what we have. So we computed Gower distances of the species based on these traits, and we used the resulting distance matrix to run a PCA and k-means in order to try to find group of species that have similar ecological roles or similar ecologies that we call here functional types. So using again the approach that we used in our previous work, we built a bipartite network. In this case, one of the nodes are the continent states and the other ones are the functional types. And of course, the connection between them. So in order to go deeper in the study of the functional evolution, we also compute a functional space. For that, we use beta diversity in terms of continent states functional turnover. A dissimilarity matrix over which we apply an MDS in order to plot it in 2 dimensions. These are the main results of this study. In A, you can see here the time. The different colors correspond to the different modules from network analysis, and here are the different continents. And in B is the functional space, again divided by the 4 different continents, and the colors correspond to the different ages. So the first thing that we notice, again, confirming the tendency that we saw in the Iberian Peninsula, is that the taxonomic structure seems to be more volatile than the functional one. Coming back to the first graphic, we are going to do we are going to go through the Cenozoic to comment what happened here. So at the beginning of the Cenozoic, all these groups, all these continents form a single module. During that time, these animals were all pig-sized browsers occupying similar regions of the functional space, until around 40 million years ago, when the first reorganization happened with the split of America from the joint module, even exploring lower regions of the functional morphospace. So during that time, it was the Middle Eocene climatic optimum with a remarkable increase in temperature that allowed to diversify and explore different regions of the morphospace and also split from the joint model. Continuing in the Cenozoic, we find here the first simultaneous reorganization, starting around 25 million years ago and ending around 21 with the first tipping point. During that moment, there were big abiotic changes. A bridge between Eurasia and Africa emerged, the Confoteriulan bridge. This also provoked the closure of the Asian Tethys Sea and the born on the Mediterranean Sea and the Indic Ocean, with a huge effect over the environment, of course, over the species that live on it. The connection of two land masses separated until the moment brought about the homogenization of the faunas, finding a common functional structure. The animals, well, for the first time, interestingly during that time, proboscideans could go out of Africa for the first time, and several groups of Eurasian mammals could go into Africa. So the animals found new environments that allowed them to diversify and explore new opportunities. As we can see here, since the first split of America, it will follow their own functional history that will last until our current days. After that moment, the system experienced one very long period of stability until it reaches the second tipping point, around 10 million years ago. During that moment, there was a huge aridity increase worldwide which ultimately finished with the spread of the C4-dominated grassland. These new environments especially affect to the animals that feed on grass that had to adapt to cope abrasion. Another abiotic event that happened during that time, it was the birth of the Sahara Desert. This becoming a natural barrier, isolating the faunas from Africa and Eurasia, also facilitating their split from the joint model that they formed before, that we can see here. After that moment, the system gained a third period of stability that would last until current days, overcoming even several abiotic crises that happened during that time, for example, the Messinian salinity crisis or the Plio-Pleistocene glaciations, even the decay of megafauna with the potential roles of humans on it. However, the system is resilient enough to overcome all of these challenges and remain stable in terms of functional structure. But what was the role of functional diversity in these transitions? So using the same database that we used before, along with the ecomorphological traits, we calculate the functional diversity of each continent stage. Here are the results from the analysis using residuals of Shannon index. On the left, you can see the plot is always X is the time and Y is the values of the Shannon index. On the left, in the green color, is a global curve, and on the right is decomposed by continents that corresponds to the different colors. So at the beginning of the Cenozoic, we can observe an initial increase in functional diversity. As we saw before, during that moment is where these animals start to explore different regions of the functional morphospace that allow them to diversify. Interestingly, we can see here how this tendency starts in America first, and then the rest of the world will follow. That did coincide with this early split of America that we saw in the functional structure. Coinciding again, as I told you before, with the middle Eocene climatic optimum with this huge increase in temperature that happened during that time. Continuing during the Cenozoic, we reached the first inflection point with an acceleration of this functional diversity increase, coinciding with the Gomphotherium land bridge. So this bridge that produced this connection of these two land masses allow the faunal interchange of Eurasia and Africa for the first time in this epoch. So this caused an ecological enrichment with all the continents gaining functional diversity. As we saw before, this also coincides with the functional structure reassembly. So after that moment, the system starts to accumulate species inside the same functional types until it reaches a collapse due to ecological redundancy around 10 million years ago. During that moment, as I was telling you before, there was a huge increase in aridity. We came from a humid forest environment and we have a transition to a more arid world, more similar to what we have today in our current ecosystems, which also have the spread of the C4-dominated grassland during that time. In this case, we can see how this pattern started in America first, and then the rest of the world will follow. So this decay didn't stop here. even reaching a third inflection point, accelerating this decay around 2.5 million years ago, coinciding with the beginning of the Plio-Pleistocene glaciations. There was a huge effect these faunas and provoked their continuous decrease in functional diversity. However, as we saw before in the functional structure, the system seems to be resilient enough to overcome this continuous decay in functional diversity with no apparent change in terms of functional structure. Interestingly, if we take a look on what happened to America at the end of the Cenozoic, they were gaining functional diversity where everyone were losing. So this could be related with another abiotic event that happened during that moment, that was the Panama Isthmus formation with the Great American Biotic Interchange. There were a faunal interchange between North and South America that provoked the increase in functional diversity of these faunas. So I would like to tell you about another study that we did last year, I think, that maybe you are more familiar with, which is using food webs. We use again the database that we collected for the Iberian Peninsula mammals during the last 20 million years ago, and we use the localities that they were in the three functional faunas. Just to remind you, were the localities that form these faunas that was moment of prolonged functional stability. So for that, we built one trophic network for each locality, and to do so, we use a prediction model of predation interaction, which estimates the likelihood of a species feeding on another based on body mass ratios. Besides, we calculate, once we have these trophic networks, we calculate several properties of the networks in order to characterize them. So the thing that we found is here in this plot. So the x-axis is the age, and the y-axis then correspond to the different measures that we take the properties: the predation pair ratio, connectance, mean degree, and interaction diversity. So the thing is, we found that these networks become more sparse as simplified towards the present. You can see clearly see here this in looking like how the predator prey rate increase, the connectance, mean degree, and interaction diversity decrease through time. You can see also here how the low connected predators increase during this time frame. So what happened there? We know there were a huge aridity increase in Europe, especially in the middle Miocene during that time. This provoked an increase of the emergence of large body herbivores and a decrease of mid-sized species. So this caused a change of the prey species communities, increasing the extinction risk of these predators. So to wrap up, we developed a new analytical approach based on network analysis to characterize ecosystems. We found that functional structure experienced long periods of stability interrupted by rapid change, where only major abiotic changes could push the system out of an ecological threshold, forcing a functional reassembly. We found that the functional structure tends to endure longer than the taxonomic structure, so conservation actions oriented to preserve this functional structure will tend to endure longer in our world ecosystems. Regarding the food webs, we saw how change in prey composition of the prey species pool increase the extinction risk of predators. So when we are developing conservation strategies, we should look beyond individual prey species and also take a look on the community composition of this prey species pool. So before finishing, you might wonder why I'm here and what is why paleontology matters for an institution like the EBD, right? So I can summarize this in this sentence. So we need to understand the past in order to comprehend the future, the present, and model to the future. So we need to understand what happened to the biodiversity in the past, how they respond to prolonged periods of climatic change, even mass extinction, in order to understand why the species are in the status that they are today. And using a combination of current data and deep time data, we can better feed predictive models in order to anticipate the responses of the biodiversity to current, to ongoing climate change and also future change. Another thing is how these connect with the EBD research line. So I just select some of them that I have, that I think that they have some synergies with my background. For example, the evolutionary patterns of processes. We need the deep time perspective, which means the fossil record, to fully understand the evolutionary patterns and processes. Without that, we cannot fully understand why this happens and the consequence of this. Regarding ecological interaction and maintenance of biodiversity, applying network analysis to both fossil and extant system could help us to understand the situation, the current situation of our world ecosystem, and of course to develop more efficient conservation strategies. Regarding global change and biodiversity conservation, the fossil record is the only window that we have to see how a species respond to prolonged climate change, even mass extinction. So we need to take a look on the fossil record to see how these species respond in order to understand how the current species are responding the way that they are and how they are going to respond in the future. And lastly, theoretical and computational ecological evolution. Today, I only talk about one of my main research lines, but I also work with machine learning and ecological modeling, which integrates the paleontological data with climate emulation to find factors of fragmentation, for example, of a warm temperate forest, for example. So last but not least, what I'm doing here. I'm working currently since October. Vicente Garcia Navas, and we are studying the functional structure of neotropical superstim, which are these beautiful birds. For that, we are going to apply network analysis to characterize the functional structure of these species in the biomes that they occupy in the neotropics. Besides, we are going to calculate the functional diversity and compare with the taxonomic diversification. All of this will shed light on the evolutionary dynamic of this interesting group of birds. So just to finish, I would like to say thank to all my collaborators, the institution for the funding, Vicente for bringing me here, and all of you for coming. Thank you.
Thank you, Fernando. Nice talk. Do we have any questions?
Thank you for the excellent talk, Fernando. I'm very happy to see that end of the middle Miocene thermal optimum also shows up prominently in your research, because I'm studying also the onset of the reorganization episode. But my question would be, so you showed the punctuated equilibrium as largely being driven by the climatic events. However, I'm wondering if the factors outside of the climate and taxa that you include into your network can also be drivers, because you're probably familiar with Brocklehurst paper on mammaliform extinction. Mm-hmm. Can, for example, extinction of the large terrestrial herbivorous birds in the end of the Eocene thermal optimum be a factor that removed some of the constraints on the mammalian trophic networks?
I mean, this is a really interesting question, and I mean, this will be fantastic to could take a look on different groups and see what happened. So for these studies, we use the mammals, because the large mammals, because for several reasons. Because especially we have a lot of fossil remains. So thanks to that, we can do this kind of studies. Unfortunately, you cannot do this with other groups. For example, the birds. Birds is, we have a really good fossil record at the beginning of the group in the Mesozoic, and really good at the end. But in the middle, there is nothing, almost nothing. So we have very few data to test this kind of studies using birds, for example. We could do something similar using maybe lizards or another group of vertebrates that have like more remains. And I mean, I would love to see this published and to compare this and see if there was some kind of not competition, but some kind of effect of decrease of one group and increase on the other. But for now, there is no. We don't have this kind of studies yet.
Hey, thanks for the talk. I'm not sure I got how you get your modules. If I get it well, is like, so you have a bipartite network that is functional groups versus towards localities.
Mm-hmm.
So, and then you do a modularity analysis and you split it into modules. But how do you remove the effect of space? Because then modules could be due to space if it's localities. So it can, and you interpret everything across time, but I was wondering how you use effect of space that can create modules also. And yeah, that's it.
Yeah, well, to characterize the models, we use the InfoMap, the map equation community detection algorithm. And Iberian Peninsula, as you told, we use the functional entities and the localities. And then this community detection algorithm trying to find the models where the nodes have more connection between them than the rest of the network. And because we are working just with Iberian Peninsula, even though they weren't like a geographical effect, so the localities that were inside of the models, they weren't in the same areas even during the time period. So this is why we know that there is no effect of the geography here. And when we do the global analysis, we try to prevent for this using this continent state. So we basically gather the different localities using the international chronostratigraphic stages, which are like time bins, by continents. So we have bins by continents, basically. And we are analyzing how the functional, it's like a study of the macro scale. So we are looking at how was the behavior of this functional structure in the different continents by time.
Okay, thanks.
Well, very interesting presentation. I was wondering about all those outliers when you're showing the plots changing through time, the communities, and there was a shift. In those plots, you have quite a few outliers. What kind of, or some communities, some dots that were outside?
You mean here?
Yes. For example, those, yeah, in the yellow area in the middle, there are those orange dots, so isolated from the rest. What kind of communities are those? How is it that there are some differentiated? It seems that I would expect some gradual change through time, but I'm trying to visualize what kind of communities are those.
Well, the thing is like apparently these communities, for example, these outliers, or this one are here, they were more similar to, in this case, to the more modern ones. So they were composed by a set of ecological roles similar to the communities belonging, in this case, to the second functional fauna than to the first functional fauna. So, but we couldn't characterize in order to tell you like these were like bigger ones or smaller ones. In this functional fauna, if I remember well, it was composed by mainly by mid-sized browsers and carnivores also of mid-size. For example, this one it was of bigger sizes. But yeah, basically this is telling us that there were some communities, some localities earlier in the time that they were similar to localities, to communities that appear later.
But isn't that very strange? In a landscape dominated by some kind of communities, that suddenly in a location at a given time there's a completely different community? Seems very strange to me.
Well, this is based on the different ecological roles. So maybe even though if in this community and they are in the same module, probably they have, well, probably not, they have totally different species, but the species that they have perform like similar roles. So they have like similar kind of carnivores, for example, or arboreal animals. The thing is like they were there, it's true that they were like very few, but when we take a look on this, just basically that so that they have like similar ecological roles. So these species with similar ecological roles in the functional structure in general, but with different species.
Thank you.
You're welcome.
Yeah, thank you for your talk. Very interesting. I am also curious, as Francois, about the network analysis, because you were showing that you had bipartite networks between localities and functional groups or species. And then you are showing the change over time of the modules. But are you doing a network per time slice, or how are you doing that?
Well, this is the analysis that we didn't include time in the analysis. So this is, we run the networks using the localities and the functional entities or the taxonomy, and then we plot the localities. So we know the age of the localities and we plot it. And this is what we got. So they were ordered. But
okay,
we
so
don't. We didn't.
Each locality, you cannot have the same locality with two different strata, different timing, no? Or
If we
locality is one time.
There is some localities that they have different strata that we know the date. If there is different date between the different levels in a fossil site, we account this as two different localities.
Okay.
For example, could be, I don't know, Atapuerca 1 and Atapuerca 2, for example.
Okay.
Because it have different age, even though they're in the same size, they are different localities because maybe there is like hundreds of thousands of years between one of them.
And you cannot have two localities with different fossil register, but that are simultaneous in time?
In the same area?
In the same, no, not the same area. Like you have a from the Miocene from one side and another Miocene in another side. You don't have that?
Yeah, well, for example, you have here
and you have, okay,
three in the same time, yeah, with similar ages, but from different parts of, in this case, the Iberian Peninsula.
Okay, thank you for that.
You're welcome.
Thank you very much for the talk. As for the outliers, I think that, I don't know if you know that InfoMap has one regularization mode or the solution landscape. I don't know if you have been playing with that options, but maybe they can explain a bit more the outliers, and maybe they can be something in, I don't know, some transitional nodes or something like that, and maybe they can be useful for you for explaining them. I don't know if you know.
Yeah, I don't know when we did, because we did this 4 years ago or something, but 5 already. I don't know if we use that for that implementation of InfoMat for the transitional node, but what we did is to check the transitional faunas, for example, to say that it was like a punctuated ecological equilibrium, that we saw that it was like an abrupt change instead of a gradual one. But I think that we did not use InfoMat in order to check that. That's a good idea. Maybe, yeah, I will definitely take a look at it.
And
thank you.
And I don't know, maybe for, sorry, if I understood well, in one of the situations you did a PCO plus a k-means for classifying.
Well, in the other, yes.
It's in the other study. As you are using network analysis most of the time, have you thought about using the network analysis for identifying the number of clusters? In that case, everything is in the same theoretical framework? Actually, we did. So basically, we try from, I don't remember, like from 0 to 200 groups in the k-means, and then we run the network number. Now the number of groups that we have here, about 120 something. When the code length starts like to get flat the curve. So we use, again, yeah, as you said, like network analysis in order to find the optimal number of clusters. Yes, and congrats.
Thank you.
Hi, it was just a couple of questions. So first, I love your idea of ecological punctuated equilibria. However, you found that taxonomy is functionality is on ecstasy, right? I was wondering, does imply that the punctuated equilibria sensu Stephen Jay Gould is not applying to your system?
Well, actually, I remember when the first paper came out, we have a bit discussion with Neil Ers on Twitter, and well, yeah, he was focusing or telling about the specific about the species, right, or the status of the species. But this is why we are talking here about an ecological, punctuated ecological equilibrium. So it's basically the same, but it's a different scale, right? It's like seeing evolution and macroevolution. Here we are seeing the system of a more macro scale, so we are taking a look on the function. So the thing that we saw is that the functional structure, the roles that these species perform in their ecosystem remains stable for longer periods, and there is some moments that something happened that seems to be related with big abiotic changes and force the system to do a reassembly until they find another stable state. So I will say that it's in line with Gould theories, but it's looking into different scales, an ecological scale, we can say.
Or different axes of biodiversity, I would
Yeah.
say. The other question I was wondering is how functional are your functional assemblages? Because, I mean, to me, function is normally related to abundance, right? So a species can have a strong functional impact on an ecosystem. Density is very abundant, or not. We have the keystone species that have a strong impact in the system at very low abundance. However, I was wondering, how can you accommodate the uncertainty in the fossil record?
Yeah, that's a really tricky thing.
To picture now landscape.
So we can say that abundance is like a prohibited word in paleontology. Because we work with what we have, right? We have some occurrences of some species, but we cannot be sure, or it's difficult to know the abundance of a single species, right? How species live in a certain point of the time in a certain area of the world. There is some mathematical model that you can do, like in order to prevent that. But in paleontology, the way that we understand the functional traits is traits of the species that allow them to have an impact or an effect in the ecosystem. So that define their needs, for example. And for the first study, we decided for diet, locomotion, and body size, because these are traits that are widely used and they define well how the species perform in the ecosystem. In the case of the large herbivores, since we can collect more reliable data, or not more reliable, but more detailed data, we follow the works by Michael Fortelius and Indre Thirobaite that they develop what they call ecometrics, which are dental traits of herbivores that have a direct relation with the environment. So they did studies in African parks, and they found these 13 traits have high probability to infer the climate where the species live. This is why we decide to use these 13 dental traits in this case of the worldwide analysis, plus also we add the body size, because we think that the body size, and it demonstrated in several, not just paleontological, but in ecology and biology, that the body size is one of the main traits that have like importance in how these species perform in the ecosystems. So this is the rationale behind why we decide these functional traits and not others.
Nonetheless, I guess that if a species is leaving a footprint in the fossil record, that there is a high probability that the species was very abundant, because rare species are less likely to leave a footprint, right, in the fossil record?
Yes and no, because also there is also the chance. So in the fossil record, there is a lot of chance. So maybe, so just to have a fossil is like something so unique. So you have for example, here in Sevilla, you have all the biodiversity that is here, right? So in the fossil record, we have only a fraction of that. And doesn't mean that if a species fossilized was the more abundant. Like in principle, I would say yes, but it could be like this. For example, there is some carnivore traps, right? Like caves, when it was like an animal walking around there and then fall into the trap and get fossilized. That means that was the most abundant? No, that means that this animal was there. Exactly, or they on the max extinction events, for example, something like. It's different when you have like these high resolution fossil site that they call Lagerstätten, when you have like a massive extinction event at the same time, and you have fossilized like almost everything that was in that moment in that area, right? There you can have an idea or a better idea which taxa were more abundant than the other, but in general, it's difficult to translate that if we found a taxa, we can say that it was more abundant than the others, tricky in paleontology.
Yeah. It's terrible for you.
Yeah.
Congratulations. Thank you very much.
Thank you.
Question. I was just curious, in your data sets for the Iberian Peninsula and also for the world, how many species do you tend to have in a locality, like in one of these, what becomes one dot? Because we're talking about these sample sizes and the chance of having a fossil, what's a typical number of species?
The typical number? So on average, you mean?
Like, yeah, that contributes to 1 point in your data set.
Well, the thing is, like, we use several sample standardization methods in sensitivity analysis, because, of course, when we are working with paleontology, we cannot rely that the thing that we are finding in a fossil site reflect the biodiversity. So we only select some richest localities, but on average, I don't know, I think more than 20 species per locality. Thanks. Between the two, more or less.
Yeah, thanks. So you stressed twice the value of your research for conservation. Can you give us an example about how you're going to transfer all this into specific conservation actions for today's problems?
So the idea is not a direct translation, but to inform the people, the researchers that are working in current conservation. For example, using the food web analysis, we found out that the thing that increased the extinction wasn't the extinction of the individual prey of a species. It was a change in the composition of the prey species pool. So with that, we can tell, well, we already did, to the people working on this, and they should look beyond to preserve just an individual prey species and look more about the composition of the species pool, right? So this predator maybe is predating of, I don't know, 10 different species. So maybe we have to focus on preserve the pool of the species, or the proportion of big and small prey, more than just focusing on one of them.
No, I'm just considering, how the manager will take that.
Yeah, I mean, it's difficult, of course. I mean, this is just the beginning, like just the first stone, right? So as I told you at the end of the talk, is just try to understand what happened to the species and how they respond to plus climatic changes, right? In order to understand why the species are where they are in the world, and how they are now, right? In the number of they are, how many groups they have in the past, why they were so abundant in the past. For example, the terrestrial large herbivore, why they were the case of Probostidians, right? There is a moment around, I think the peak of diversity of Probostidian, it was around 4 million years ago, with 25 species living at the same time. Today we have 3. So why? We need to understand why in order to better implement conservation strategies to the few species that we have today. So just asking your question, there is not a direct application of in conservation, but more like try to a stone that help us and help the people working in current conservation to have more knowledge about what happened, that will allow them like to find better conservation or more effective conservation strategies.
so we can wrap it.
I think there is a question there.
Last and very simple. First of all, it was a very beautiful presentation. Thank you very much.
Thank you.
Of 4 continents, and Oceania is absent. So I was just curious, is it because it doesn't have paleontological value because of the absence or the limited fossil fuel records?
So I would love to include Australia on this analysis, but the problem with the Australian fossil record is very scarce, so there is no much. And the things that they have, they are not studied enough. So there is no available information. Every time that I go to a paleontological meeting, I always talk with people working in Australian fossils because there is few of them and there is it's an ongoing work. But I hope that in the future we have available data to include Australia because it will be fantastic, like the special case, right, of Australia as an island for most of the evolutionary time. But we know that there were large herbivores there in South America, in Australia, sorry. But we couldn't include it because we didn't have the data.
So it's not about absence, it's about the absence of investigation in the...
It's both. There is no so much fossil size in Australia, and the few that they are really poor study. So they need to work more on the study of the fossils and publish this data, and then we will be able to use it. Yeah.
Thank you.
You're welcome.
Okay, if we do not have more questions, last chance. No? Okay. So let's thank Fernando again.